So you were asked to do this on the test, right? And one of the things I always find is that students just don't know what the first step should be. And the other thing is students think that they need to add reagents. And in these problems, they're just reactions, and you just have to, with what's given, figure out what the product is. How do you get the product? It's a question about drawing arrows. So the first thing to think about is what's the first step. So let me draw this. I'm going to draw it in a way that is a little more conducive to mechanisms anyways. The only reagent you're given is what? H2SO4, right? So probably that's the first step. And one of the things I said last semester is if you have H+, it's probably the first step in the mechanism, protonation. Right, no, a lot of people do this. So I'm just going to call it HX, but H is the HSO4 minus, okay? And then now you have to decide which one of these two things to protonate, and that's the difficult thing, okay? Sometimes you have to do both and see how it works out. So it turns out to be this one. And I'll tell you how you might know that. You might know that because when you look here in the product, this oxygen's missing. And so what you're doing is making a good leaving group. So you just have to look at the product, look at the reactant. If you do the other one, it's possible that it's the other one. So what happens is that you take your first guess, you try to do the best you can with it. If you can't get to the answer, you take your second guess and you try to get to the answer. And if you can't do that, probably you're running out of time. So it's a test, right? If it's homework, I assign these things on homework sometimes, right? If it's homework, you should take as much time as it takes to figure out like how it's happening. But understand why you're doing it. Okay, so like this first one, you have acid, you're going to protonate, so you're going to protonate one of the oxygens because this is what usually protonates. And then you're looking at the product and you say, well, the tertiary alcohol, that's the oxygen that disappears, so I'm going to protonate that one, and then I'm going to make it a leaving group so it goes away. So that means I have this. And I protonated to make it leave, so now I'm going to make it leave. And that leaves me with a carbocation. And that's a good carbocation to have because it's tertiary and it's stabilized. Now there's two routes like you can go with this. One is you can get a hydride shift. And the reason you can get a hydride shift is because it's stabilized by resonance through the oxygen, okay? That's one possibility that I gave credit for. And the other one is just an elimination reaction. And that I also gave credit for that, okay? So the hydride shift, you can envision it as, and actually some people actually did this in 2 steps. You can do it in 1 step. Like that. So that actually gives you something very close to the product already. And then it's just minus H+. So base, whatever the base in solution is, could be one of the alcohols or something. That leads directly to the product. Does that make sense? So a hydride shift forced by the oxygen resonance, that's what stabilizes it. The other possibility is there's an elimination reaction. And so if you do the elimination reaction, you get that. What's that? That's that functional group combination. has a name. What two functional groups do you see there? Alkene and alcohol. So you guys remember what it is? We haven't done too much with it. Just a little bit. It's in the alcohols chapter, of course. It's an enol. And when you have triple bonds and you hydrate them, you form enols. And enols tautomerize, they rearrange to that. So it's not an equilibrium. But these guys are tautomers of each other, which means you can just rearrange that double bond and shift the hydrogen. We haven't learned the mechanism for that, so if you didn't do it, I was kind of okay with it. The mechanism's not hard, but it involves a lot of steps. One is this. I don't like having negative charges under acidic conditions. So what happens is it just does this. It goes to an H plus, often H2SO4, so it attacks, it's a protonation reaction from sulfuric acid. And that essentially gets you back down to this position here. Okay. So I think the easiest one is just to show it does an elimination, and then you remove the proton. But they're essentially like merging, those two mechanisms merge at that point. And I gave credit for things that were pretty close to this too. There was like little minor details, as long as they weren't like gross errors.